Stanford University.
We haven't discussed units at all, and let's discuss units a little bit. In hadron physics, we've discussed the idea that a hadron is a string and that it can be excited. That it can be excited by setting it into rotation or setting it into vibration, by exciting the harmonic oscillators that make up the stringy character of the proton or whatever it happens to be. There's a certain energy scale or a certain amount of energy that each excitation will give you. In particular, the energy jump from the ground state to the first excited state. How much is it? What does it depend on? Well, in a string theory, there's really only one parameter. We talked about it a little bit. We discussed the idea that if you stretch a string, let me just go back a little ways. If you stretch a string from one point to another, then it behaves pretty much like a spring. It does behave like a spring. It has an energy, if this is a non-relativistic string, just an ordinary non-relativistic string, a rubber band, or an idealized rubber band, its energy, its potential energy, let's call it E. What does Hooke's law give for the energy? Some k, which is some spring constant, times the square of the distance between the endpoints. Missing something, factor of 2. Okay. Yeah, that's the potential energy that's in a string, and we've identified energy, this non-relativistic energy, we've identified it not with the mass of the string, but with the square of the mass of the string. Why? Because we're thinking about this in a frame of reference where the string is moving very, very fast, and where non-relativistic physics actually works for the motion of the string perpendicular to the direction of motion. So let's keep that in mind. We're looking at a string that's going down the z-axis like this. It's been stretched to a distance x, or let's call it L. Distance L, this becomes L squared, and we've identified the energy with the square of the mass, L squared. There is some spring constant, okay. That spring constant I'll just call K. It says that the mass of the string, which in the rest frame, in the frame of rest at which the string is at rest, that mass is the usual energy. That's going to be the square root of that spring constant times L, perhaps divided by the square root of 2. I'm not interested in square roots of 2 now. So the mass of a stretched string is proportional to its length times some parameter, which I've called the square root of K. The square root of K has another name. It's called the tension. It's the tension in the string, the energy per unit length. Take a mass, then we have a string at rest. We're not looking at it in this frame in which it's moving fast. Its energy is its mass. We stretch it out, and the energy of it grows proportional to the length. It's like surface tension, except now it's linear tension instead of surface tension. Energy proportional to length, the coefficient is called tension. It's the tension in the string. And so there's a tension which is just the square root of K. We don't even need to call it square root of K, we can just call it tension. All right? Now, how much energy do we get for each oscillation, oh, yeah, what are the units of the square root of k? Let's work in our favorite units in which the speed of light and Planck's constant are equal to 1. In those units, energy has units of 1 over length. So if energy has units of 1 over length, what's the units of kappa here, or square root of kappa, the string tension? Yeah, it's energy squared, or 1 over length squared. Energy squared, if you like. So this object over here, let's call it T. T for tension. That tension in the string is the thing which sets the fundamental scale and it sets the scale for everything. It sets the scale, it has units of energy squared, and I'll tell you what it does. It tells you that each excited state, each time you excite the string by 1 unit, it adds to its mass squared essentially that tension. It adds to the, so the thing which has units, the thing which determines the units of the theory are this string tension. The bigger the string tension, the bigger the jump in mass when you excite something. The same thing is true of an ordinary spring, incidentally. If you have an ordinary spring, let's take the mass of the spring to be 1, the spring constant, call it k. The frequency is just, well, it's the square root of k over m. The frequency is proportional to this tension. And of course, the energy that you bump up the spring by every time you excite it is also proportional to omega. So the energy jump between the ground state, the first excited state, next excited state, and so forth, is controlled, the unit is controlled by this string tension. Okay, you could ask, what is the string, and string tension is force per unit, is energy per unit length. You know another name for energy per unit length? Energy per unit length. Force. Force times length is energy. Force times work, force times distance is work. Right. So all this tension is if you pull this apart, that's how much force is pulling you back. That's how much force is pulling you back. It's the force within the string. Another way to say it is if you took one of these strings at the surface of the Earth and you anchored it at some place and suspended a weight from it, it would be the weight that the string could support. A heavier weight would just shrink or would fall down. A smaller weight would be pulled up. Okay? That's the character of these strings. If you had one in the laboratory, the force, the weight that it can support is independent of its length, incidentally. You see that from this formula. You see that from the formula that mass or energy, same thing, energy is equal to spring or tension times length. Force is energy per unit length. Energy per unit length is force, and so the force that this string can support is independent of its length. That's the character of these strings. Okay, so then you could ask, how much weight at the surface of the Earth, how much weight could a hadron, a meson, if you could somehow anchor one of the quarks in a meson to some support over here, the ceiling, how much weight could a meson support? And the answer is about a truck. about I can't remember if it's an 18-wheel truck or a 16-wheel truck, or maybe it's just a half-ton panel truck. I don't remember, but it's that order of magnitude. That's what a meson could support. Okay. So they're pretty strong. They're microscopic little things, but they're pretty darn strong. And the stronger they are, the higher the frequency of the oscillations, and so the larger the gap between the lowest energy state and the highest energy state. How do I actually know this? Did anybody ever support a truck with a hadron? Of course not. What we actually know is the amount of energy that it takes to excite string. And from that we deduce what the tension is, and from the tension I can then tell you what you can support. These are not the strings that string theorists imagine are associated with really fundamental particles like gravitons, photons, and so forth. Those strings are much, much stronger. Very much stronger. The tension in them is vastly larger. If, again, you took the Earth and you supported a weight, namely the weight of the whole galaxy. Now, of course, this is nonsense. It's not the galaxy that's going to move, it's the Earth that's going to move. But if you could concentrate a mass of the galaxy in some small volume and make the Earth heavy enough, now you say if I make the Earth heavier, I increase its gravitational field. Well, not necessarily so. We can make the Earth much bigger but keep its gravitational field the same. If you could somehow keep the gravitational acceleration, the acceleration due to gravity, the same, then the weight that you could support would be about the weight of the galaxy. So the strings that we're talking about in fundamental string theory are vastly higher in tension, much higher in tension. The meaning of that is that the energy in an excitation to excite the string is much, much larger. These are much stiffer strings. They have much, much larger spring constants and therefore much larger frequencies of oscillation. If larger frequencies of oscillation, then larger energies in exciting them. How much energy? Well, the thinking goes that it's probably somewhere up near the Planck energy. If we're talking about gravitons, it's the gravitational scale. Does everybody know what the Planck energy is? I know you've heard of it. Do you know actually what it is? First of all, in numerically, and second of all, what it actually, where it comes from? Yeah. Times c squared. Right. That's a fairly big energy. It's enough to. That's a car bomb. Boom.
How much was it? I didn't hear.
Hmm?
I didn't
How
hear
much? We didn't hear it.
10 to the minus 5 grams.
10 to the minus 5 grams. And then you take that and square and multiply it by the square of the speed of light. Right. But when I asked you if you know what the Planck energy is, or the Planck length, or the Planck whatever it is, I was asking a more theoretical question. I was asking, do you know what it is in terms of the other constants of nature? Maybe we should go through that. I mean, this is worth doing.
Also, how long are these strings?
Okay, no, that's the other question. That's the other question. The stiffer they are, the smaller they are. Now, of course, you can stretch them out to any length. There's no limit to what you can stretch them to. But if you ask how much in their ground state, remember, things in their ground state oscillate. How much do they oscillate in their ground state, and what's the mean fluctuation in the size of these strings, the vibrations of them? Then the larger the spring constant, the smaller they are. They're much stiffer, much harder to pull apart. Pulling this thing apart by 1 centimeter may cause will cause a lot of, the smaller, the bigger the spring constant is. All right, so how big do people think they are? Oh, somewheres of order the Planck length. The Planck mass, the Planck length. How fast is one vibration? The Planck time. Okay, so let's talk about these Planck units. There's some reason to believe it's a little bit smaller than that. Maybe a factor of 10, maybe a factor of 100 smaller, but that's a fine point. So let's talk about what the Planck length is. I didn't prepare this, so we're going to have to work it out in real time. What is the Planck length? What are Planck units, first of all? What are any units? In physics, we need to have 3 units: mass, length, and time. And our usual choice of units is the usual units that we use in the laboratory are not determined by any fundamental physics. The meter is a convenient unit for measuring rope, okay? That's where it came from, measuring rope. You measure rope like that, or cloth, or whatever it is. So no doubt it originated from the length of a human arm, probably. A foot, of course, is also a similar kind of unit, and it, I assume, came from somebody's foot, the king's foot. So what's the real physics then, or what's the real science of what a meter is? The real science is how many atoms does it take to make a length of an arm, a useful arm. It has nothing whatever to do with any fundamental physics. It has to do with biology, how long it takes to make an arm. Not a very deep unit. That's mass. Mass, same thing. A kilogram is a kind of weight that you can manipulate in the laboratory. And a second is about the time that you could measure with a pendulum. That's it. That's where they came from. And they have no deeper meaning than that. We would like, for really fundamental reasons in physics, to choose units which have some very fundamental meaning. Now, for example, and if we do, then many of our equations will be much simpler. For example, if the size of a proton comes into various equations in nuclear physics, and the size of the proton is 10 to the minus 13th centimeters, if we work in centimeters, or 10 to the minus 15th meters, there's going to be 10 to the minus 15th all over. And it's not just 10 to the minus 15th. There's 1.73498, and physics is going to be very messy. On the other hand, there's nothing to prevent us from saying, let's use the unit in which the radius of the proton is exactly 1. Then nuclear physics will turn out to look a little bit simpler, and it will. Nuclear physics will turn out to be a little bit simpler, but atomic physics won't look a hell of a lot simpler. The physics of subnuclear particles, subhadronic particles will not look a lot simpler. There's nothing universal about the proton. The proton is just some particle, that's all. Why use the proton instead of some other particle? No good reason. So there's nothing really universal about the proton, and the rules of physics will not in any way be especially simple if we use the proton. Time, same thing. So we would like 3 units which have some deep fundamental significance. It's equivalent to saying we would like to choose 3 constants of nature and set them equal to 1. It's completely equivalent to choosing 3 units, to choose 3 constants of nature and set them equal to 1. Constants of nature now mean dimensional constants. Right? The size of the proton is 1, but that's not a good one. You want to use things which really are very universal, 3 constants. There are 3 constants in nature which are truly universal, and I'll tell you what they are. The first constant is the speed of light. Why do I say it's universal? Because there's a rule, and the rule is nothing can move faster than the speed of light. Nothing. Every velocity of every material object is bounded by the speed of light. The use of the word every there tells you there's something fundamental about it, that there's something Whether it's protons or electrons or photons or anything else, they all are bounded by the speed of light. So there's something universal about the speed of light. Yeah.
Well, I think that the constancy of the speed of light is,
The constancy of it? Well, yes. Yes. The fact that it's the same in every reference frame, and the fact that it's the same for all particles. Now, when I say it's the same for all particles, you say, wait a minute. Protons don't move with the speed of light. The limiting velocity for a proton is the speed of light. So in that sense, it's very universal. So that's the first thing. We want to set c equal to 1. Sounds like a good thing to do. And we do that all the time, of course. The next thing, which is very universal, is Planck's constant. Let me give you an example. Planck's constant is not just some any old constant like the radius of a proton, but it's connected with the uncertainty principle. For every object in nature, the uncertainty principle between the momentum and its position is greater than or equal to h bar. There may be some 4 or some 2 in there, I don't remember. But it doesn't matter what object you're talking about. You could be talking about an electron, you could be talking about a proton, you could be talking about a bowling ball. They are all constrained by the same uncertainty principle. And so in that sense, h bar, and it doesn't much matter whether you use h bar or h, the one without the 2 pi in it. That's not the point here. The point is that Planck's constant applies to everything in the world. It's universal. So the next thing you might want to use, not might, but we will, is to set h bar equal to 1. So what's the last really universal? Is there another truly universal constant? The gravitational constant. Remember, according to Newton, every object in the universe, no matter what it's made out of, no matter what it is composed of, every object in the universe has a gravitational force, which is the product of the masses divided by the distance squared times the universal constant g. So again, something which applies to everything. Are there units in which c, h bar, and g are equal to 1? Now that's the same as asking the question, can you combine c, h bar, and g into a combination that has units of mass? Can you combine them into a combination that has units of length? And can you combine them into a combination that has units of time? And the answer is yes. Let's see. Let's do length. We want to do length. Tell you what, even better. Let's do length squared. Let's see if we can find a combination of g, h bar, and c which has units of length squared. Okay, so here's what we do. Just some simple dimensional analysis. Everybody here knows how to do dimensional analysis? Okay, we'll do some simple dimensional analysis. We want to find a combination g to some power, let's call it p, h bar to some other power q, and c to some other power p, q, r, which has units of length. I'm going to choose length squared. Let's say has units of length squared. Now this doesn't mean it's equal to length squared. It means it has the same units. Sometimes people put a bracket around a thing like that to indicate its units. The units of g to the p, h to the q, c to the r should be length squared. I'm choosing length squared to avoid a square root in the final formula, that's all. All right, there is another reason. It is widely believed that the fundamental unit is a unit of area, not a unit of length. But we'll come to that some other time. But let's see if we can find p, q, and r. Okay, first question is what? Now we have to figure out what the units, the conventional units of g, h bar, and c are. The units of c, that's easy. What's the units of c? That's length over time, right? What about the units of Planck's constant?
Momentum distance, or mass velocity.
Energy per second.
L squared m over t.
Again?
L squared m over t.
Yeah,
Where'd you get that from? I don't even know what to say,
Squared
but-
mass.
momentum,
Momentum times distance, right? Delta x, delta p. Delta x, delta p, so that's a length. And then a momentum is a mass times a velocity. And a velocity is a length over time. So that's length squared over time. Length squared mass over time, that's Planck's constant. And the last one, the one that I can never really remember, these two I remember, the one I can never remember is g. But how do we figure out what the units of g are?
acceleration equals mass times g times.
Yeah, we use one of the equations that g appears in. All right, so so here's an equation that, let's see. Which was your equation?
Acceleration distance.
All right, acceleration equals, yeah, we'll get that in a minute, but it's equal to mass g over r squared. So that's length squared. Acceleration is what? Length per time squared. And again, equal means, doesn't mean equal. So it's L cubed over t squared divided by m, it looks like, huh? Right? Okay, let's now go through the exercise.
Can I say something? By the way, that's like Kepler's law where the amount of
You're right.
area is.
You're right. You're right. It is like Kepler's law. Okay. So now we have on the left side length squared. Now let's go g to the power p. What's g again? All right, so it's L cubed over t squared times m in the denominator. All right, so it's L to the 3p, t to the 2p, m to the p, right? Did I get that right? That's g to the p. Now what about h bar to the q? H bar to the q is length squared, length to the 2q, m to the 2q, no, m to the q, and then t to the q. Did I get that right? Okay. And then the last one is speed of light to the rth power, which is length to the r over time to the r. Now all we have to do is find three constants so that everything on the right-hand side cancels out except 2 powers of length. Okay, so the first thing you can see is mass only appears in 2 places, mass to the q and mass to the p. So what does that say? It says p better be equal to q. Okay, so let's just set p equal to q. We now know that, and we can cancel out the masses. That's done. Now, what else do we have? We have to get rid of all the times, it looks like, huh? All right, so how many times do we have? We have 2p plus q is the same as p, so that's 3p plus r equals 0. 3p plus r is equal to 0. So that tells us that r is equal to minus 3p. Did I do that right? Let's just check. We have 2p, 3p plus r equals 0. R equals minus 3p. Okay, I hope I'm doing this right. Minus 3p. Did I make a mistake? Yeah, but Q is P. We've already figured out the Q is P. So if I'm not mistaken, I think we can get rid of all the T's. P is equal to Q. So let's see what we have. We have P is equal to Q. That looks like 5P. Boy, do I not recognize that. 5P. L to the 2Q, that's taken care of. And now R is what? R is equal to minus 3P.
Yeah, and you're done.
Oh,
Yeah, 3P minus 5P is
Yeah, you guys,
Yeah.
so 5P minus 3P and you're done.
2P.
R is
we get
minus.
2P, right? We get 2P. Altogether 2P. 2P. And that now tells us what P is. P is equal to 1. Okay? So let's see what we have now. P is equal to 1. It tells us that the Planck area, this is the Planck area. The Planck area L squared is G H bar looks like over C cubed, right? C cubed. C cubed. This is usually expressed by saying the Planck length is the square of this. Okay. The square root of it, thank you. Should we put in some numbers? My problem is I can never remember what Planck's constant is. Anybody know Planck's constant? 10 to the?
1 times 10 minus 34
Good. 10 minus 34? Oh, okay. Yeah, G is 6 times 10 to the minus 11, which is about 10 to the minus 10. Order of magnitude 10 to the minus 10. What is H bar? 10 to the minus 34? 10 to the minus 34. In usual MKS units, 10 to the minus 34. And what is C cubed? C is 3 times 10 to the 8th, 3 times 3, 10 to the 17th. Oh my God, how many? Times 10 to the minus, how big is 10 to the minus 24? I think it's more like 10 to the minus 25, huh? Or 10 to the minus 25. So how many square meters is this? Pretty small. Pretty small. Yeah, some tiny number, okay? The Planck length is very small. If we had done it right, we would have gotten 10 to the minus 35 meters. So 10 to the minus, should be 10 to the minus 70th square centimeters. I'm not sure I got everything right. Yes, about 70. All right, so that's small. That's smaller than anything. What's that? Good. Okay, now the Planck time. That's the Planck length is the square root of this. What about the Planck time? Think of the Planck length as being the size of a little thingy. All right, there's a thing the size of the Planck length. What do you think the Planck time is? It's the time for a light ray to cross that thing, right? What else could it be? Right, so it's the time for a light ray to cross that little distance. So does that mean, that means we have to divide it by the speed of light? Yeah, we have to divide it by the speed of light. So the Planck length, L Planck, is 10 to the minus 35 meters. The Planck time is 10 to the minus 43 or 42, something like that. 42 seconds. 10 to the minus 44, 43 seconds, something like that. Now what about the Planck mass? We haven't figured out what the Planck mass is, but we could do exactly the same calculation, work out what the Planck mass is. From H bar, and the Planck mass would be about 10 to the minus 8th kilograms. So this one's big. That's a big mass. 10 to the minus 8th kilograms is a observable thing. It's a little dust grain. All right, it's a little dust grain. These are impossibly small, small times and small distances. Okay, this is the Planck units. Things measured in these Planck units are measured in some very, very fundamental units. Okay, I'll tell you some things. The universe has a radius, the known observable universe, the horizon size is about 10 to the 60th Planck lengths. 10 to the 60th Planck lengths. The age of the universe is also about 10 to the 60th Planck times. And good, that's a tank of gasoline is about an energy content. A tank of gasoline is about the Planck mass. Okay, so that means you could drive across the country with 10 Planck masses of energy. Okay, right, that's what it means. These are the units that string theory is in. In other words, the size of a vibrating string, the fluctuations in it due to quantum uncertainty, order of magnitude, the Planck length. The frequencies of oscillation, or the time, not the frequency, but the period of oscillation, of order 10 to the minus 43 centimeters. Sorry, 10 to the minus 43 seconds, right? And the amount of mass that would be involved in exciting a fundamental particle such as a graviton or an electron. Let's take the electron. If the electron is a string, you could ask how much energy does it take to excite it? The units are expected to be somewheres in this range, 10 to the minus 8th kilograms. Now, that's a huge number. How many GeVs, giga electron volts, is that? One other useful number to remember is that one Planck mass is about 10 to the 19th GeVs, which means 10 to the 19th proton masses. One Planck mass is about 10 to the 19th proton masses. 10 to the 23rd proton masses is, a little gram of water or something. 10 to the 19th, which is 4 orders of magnitude smaller, is a tiny, tiny little droplet, but visible, quite visible. Well, if you have good eyes. So, exciting an electron by a particle physics collision, you say, well, we don't need to do a particle physics collision. We'll just explode a tank of gasoline in the vicinity of an electron, and it'll start the electron vibrating. Yeah, it's just a rather hard to get the energy to be concentrated in such a small distance. So, these are the reasons that yeah, above its ground state. No, well, remember it's mass squares which come in integer multiples. All right, so it's mass squares which come in integer multiples. So if you want to know what the unit is, square the Planck mass, and that's the amount that it takes to bump you up. But to go from the ground state, if the ground state is almost massless, then it's about 1 Planck unit of energy.
That's why you can't excite an electron.
Right. 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 It's just much too much energy to pump into such a small volume. And, it's for this reason that that string theory is way direct detection. How would you detect that a thing is a string? The same way you detect that a proton is a string. You hit it, you set it into vibration, and you discover that there's a bunch of excited states where the mass squared is proportional to the angular momentum. That's the kind of thing you'd like to do with an electron. That's the kind of thing that you'd like to do. I'll be right with you, Michael. That's the kind of thing you'd like to do with a photon. But the increase in mass here is just way beyond what can be done. Yeah,
In order to have the structure of the string that we've been describing,
yeah,
wouldn't the string as a whole have to be somewhat bigger than this?
right. Mm-hmm. Yeah. Yeah.
Question? Question? This is just a bunch of arithmetic over here. What makes us think that when we get a number out, 10 to the minus 35th, that it has anything to do with the length of a string?
It's a guess. It's a guess. It's a guess based on a number of things. No, it's not just, no, it's not just numerology. It could be wrong. It could be 1,000 times less. Nobody thinks that the string length scale could be smaller than the Planck length. That looks quite impossible. But that the string length scale could be larger and the energy scale lower, that is possible. How much lower? Well, I think from the things that we know about particle physics, we can't say with any precision at the current time really at all. But from the precision with which particle physics, standard model and so forth seem to work, I think there's plenty of evidence that the energy scale is very, very high. Whether it's Planck scale or 1/100th of the Planck scale or 1,000th of the Planck scale, we don't know. There is another scale in physics. There is another scale in physics which keeps coming up over and over again. We've talked about it. It's the unification scale. If you remember it all from last quarter, we talked about the scale at which the various coupling constants seem to come together, the scale at which the electroweak forces and the QCD forces seem to merge into a common structure experimentally, and there are experiments. They're not experiments to get to that energy, but experiments to extrapolate. The extrapolation of what we know about physics seems to say that ordinary quantum field theory probably holds to something like a distance scale of roughly 1,000 times larger than the Planck scale. So we do have evidence that that ordinary quantum field theory, without any stringy structures and so forth, or equivalently that the electron is fundamental to scales perhaps 1,000 times smaller, 1,000 times larger than the Planck scale. But that's still pretty small. Then you wouldn't be able to suspend the galaxy. Maybe you could only suspend, I don't know, some globular cluster somewhere. But
Yeah, it seems that a Planck length can be thought of as the fundamental unit of, smallest unit of length in the Planck time, smallest unit of time.
well,
Clearly, a Planck mass is not a fundamental unit of mass.
No.
It's to define.
No. No. The Planck mass is believed to be the mass of the lightest possible black hole. One Planck area, 1 unit of entropy, and how long would it take to evaporate? 1 Planck time. Here today, gone today. Yeah.
When you showed the coupling coefficients unifying, you showed the coupling coefficients unifying. I believe one time you put down a fourth one for gravity, so that comes down. Is that
That's a connection,
associated
yeah.
with what's
Yeah.
the coupling unit
No,
for gravity?
that's, okay. I'll tell you what the various pieces of evidence are. I'm not going to explain them in detail. This is just to remind you. If you plot the coupling constants of which coupling constants, the ones that we measure in the laboratory, the electric, let's just call it the electric coupling constant, E squared really, the weak interaction, the electroweak, I'm getting a little, there are three of them. There's U1, SU2, and SU3. There are three of them. This is energy this way. And energy is the same as inverse length. Inverse length. So as energy gets large, wavelengths get short. Energy, high energy means small distance. Okay, we measure these coupling constants at some energy scales. Remember, coupling constants are things which change with energy or change with distance scale. We measure them somewheres, where in laboratories, which means 50 GeV, 100 GeV at most, we measure them here and we get three numbers. We also measure slightly indirectly the derivatives of these things. In fact, we can compute the derivatives of them. We can compute the derivatives of them purely theoretically, but with good confidence because we know the theory here very well. What we find is that if you extrapolated these, they would all cross at about a common point. That point is way, way out here at an energy which is not the Planck scale, but it's about 100 or maybe 1,000 times, somewhere between 100 and 1,000 times smaller than the Planck scale. I think maybe more like 100. So this could be m Planck roughly divided by 100, somewhere in between. And the Planck scale would be over here. Well, this is a logarithmic scale. On a logarithmic scale, it looks like this. So on a logarithmic scale, a given gap can mean a very, very big change in energy. And it looks like this. Now, of course, we don't know with certainty that there's not all kinds of things going on at higher energy here which would muck this up badly. We don't. But what we do know is that if there is nothing in here to muck things up badly, and there's some reason to believe that these coupling constants would just come together at this scale. The meaning of that is that quantum field theory, conventional quantum field theory, seems to be working to about here. There's other evidence for this scale coming from neutrino masses and a few other places, but it's far from tight. It will become much tighter if LHC is lucky and makes the right discoveries. It will become much tighter and we'll have a much better knowledge about this extrapolation. So this is one of the things we're going to learn from LHC, is how reliable this extrapolation is. Planck mass being out here. And this in itself doesn't tell us where the string length scale is. What it tells us is that the stringy character of particles does not become important until energies above this. So somewheres between here and here, if string theory is all right, somewheres in here is the scale of strings.
Remind me again what the three coupling constants are. There's, what is it, QED, QCD,
Well-
and gravity?
No, QED, QCD, and the weak interactions.
Oh, weak. Right.
Yeah.
At one point, you did put down, I think, you put down something for gravity. You put down the fourth one?
Yeah. If you were to plot the gravitational coupling constant behaves differently, has a different character. But let's see. It starts very, very small, and it goes up something like this, and it would cross. It doesn't cross at the same point. It crosses somewhere nearby. But basically, the place where this one gets to be about order 1, that's the Planck scale. So it's really exactly the same statement to say that the gravitational constant, the running coupling constant, crosses at roughly the same place as to say this unification scale is not too far from the Planck
Does that
scale.
running constant depend upon capital G?
Yes.
So does capital G change as you start to measure at higher and higher energy?
Okay, no, capital G does not change, but capital G is not exactly the right measure of things. It's capital G. All right, let's do, I'll answer your question. Let's look at the force law between two objects. In electromagnetism, it's E squared divided by R squared. and that's the force, and that's the electromagnetic coupling constant here. In gravitation, it's g m squared over r squared. So the thing which is analogous to E squared is g times m squared. But what m should you use there? Well, the m that you use there is associated with the particular scale of physics that you're studying. All right? So you can see then, in that sense, this quantity here increases like m squared. Yeah, so this is the relevant thing here. It's the dimensionless thing. Okay. That's units.
Where on that scale, if you could build accelerators big enough, is it that you start producing nothing but little black holes?
Real black holes?
Yeah, the small ones, you know, if you build galaxies. Oh, it's all the way out there.
The quark mass. Yeah. There's two ways to produce black holes. One way or another, you've got to have a lot of pressure to squeeze things into a small volume. One way is kinetic energy. Small objects with lots of kinetic energy, blast them together, and you have a chance of making a black hole. The other way is not kinetic energy, but gravitation, gravitational potential energy pulling things together. That takes a star. So to make a black hole using gravity, you need something as heavy as a star. To make a black hole by the collision of particles, you need energies of order the Planck energy. Now, if you think about that for a minute, imagine an accelerator. I don't know, is it fun to, let's explore the following question. How big, what kind of accelerator would it take to do experiments at the Planck energy, to do interesting experiments at the Planck energy? Well, basically, the energy of an accelerator, of a linear accelerator, scales linearly with the size of the accelerator. In other words, you get a certain number of GeV per unit length. SLAC is a good example. It takes approximately 2 miles to accelerate a thing to 100 GeV. So 2 miles for 100 GeV. 2 miles, 100 GeV. All right, the Planck energy is about 10 to the 17th times bigger than this. It's 10 to the 19th GeV, so it's 10 to the 17th times larger. So with just the parameters of the SLAC accelerator, you can multiply this by roughly 10 to the 17th. So it would take 10 to the 17th miles. How big is 10 to the 17th miles? Oh man. 10 to the 13th miles is about a light year. 10 to the 13th kilometers or something like that, if I remember. 10 to the 13th kilometers, 10 to the 17th, 10 to the 4th light years, galaxy size. Galaxy size to accelerate something up the Planck mass. We're not going to do it, at least not tomorrow. Okay? But suppose you could build such an accelerator. Next question, what kind of luminosity do you have to have? An accelerator has to have a luminosity. The chances of, what we want to do now is we want to collide particles head-on to make a black hole. But remember, the radius of that black hole that we want to make is itself the Planck mass, the Planck radius. So that means we've got to aim these particles to collide within a Planck distance. Well, no, accelerators don't do that. That's not the way accelerators work. The way accelerators work is you just get a lot of particles going to the left, a lot of particles going to the right, and you get enough of them so that some will collide at the distance scales that you're interested in. In other words, you need big luminosity. What kind of luminosity would you need? Oh, I don't know, let's say, what's a SLAC luminosity? 10 to the 13th particles per second or something? Anybody know? I don't know. Well, 10 to the 13th particles, but that's just, but you know, the distance scales there are pretty big. How much better are you going to have to do? I don't know, let's say 10 to the 20th particles. 10 to the 20th particles colliding, each with the Planck energy. That's 10 to the 20th tanks of gasoline per second. 10 to the 17th barrels of gas per second to fuel it as big as the galaxy. We ain't going to do it. That's what we would need to explore small black holes, and something pretty close to it to explore string theory directly, a really direct test. The question is, are there indirect tests? All right? I think the indirect tests will pretty much be very theoretical, and unless somebody constructs a very, very convincing string theory that gives rise to the standard model exactly in some very computable way, the hope of direct tests, I think, is very remote. So that's what we're facing. That's what we're up against. Okay, we didn't get where I really had intended to go. In fact, we didn't even touch on what I intended to touch on.
Professor, these extra dimensions that you had talked about, are they in the range of the Planck's in this minus 35?
Or which dimensions?
The extra dimensions of...
Yes. Yes, it is believed, again, without really terrific evidence. But again, it's the same kind of evidence. It's the same, where is it? Where is our plot of coupling constants? If there were extra dimensions, and the extra dimensions had any sizable distance, if they were at all sizable, then ordinary quantum field theory would break down when particles begin exploring the extra dimensions. The conventional use of quantum field theory, as we use it, would break down at points where the energy became large enough to explore these extra tiny dimensions. If it's true, and if we continue to get evidence that quantum field theory makes sense as it is out to these distances here, then we'll know that the extra dimensions must lie somewheres between the Planck length and maybe 1,000 times bigger than the Planck length. So exploring extra dimensions will also be something that is extremely indirect and extremely hard.
Why couldn't it be significantly, orders of magnitude less than the Planck length? What's the argument?
If it were orders of magnitude, that's another question. That's another question. There, the theory really doesn't work at all under those circumstances. Let's put it this way. If you tried to make them smaller than the Planck length, you would wind up making their mass larger than the Planck mass. Making a small thing with big mass means you make a black hole. Black hole. So if you're trying to think of strings which were much smaller than the Planck distance, and their mass would accordingly be larger than the Planck mass, you would be talking about black holes. You wouldn't be talking about strings. That's the problem. They would collapse. Their mass and their small distance would cause gravitation basically to turn them into black holes. So that's the reason that string theorists do not ever consider the possibility that the string scale is smaller than the Planck mass. And I think it's a very good reason.
Did you say that the mass here is derived from the choice for L and T?
From the what?
Well, you gave us why we have an L and why we have a T.
Yeah, but you do exactly the same thing. You say, let's make a mass squared out of these parameters here, and I forget exactly what it is. We could figure it out.
But the others were a physical choice.
Sorry?
The other length of time were a physical choice.
What do you mean they're physical? They're all physical?
Well, yeah, but I mean, it was, the time, for example, is the time to cross
Yeah.
a length.
Yeah.
And that's a physical quantity.
Well, H bar is a physical
Well-
thing too.
And what did you say about mass? You just put it down.
Well, you get,
Does it follow from our choices from L and T?
Yes, it does. Well, no, it doesn't follow by itself from L and T. But if you asked Good. Let's see.
Once you have L and T, you can get mass from either H bar or G. Yeah.
You could ask, here's the way to think about it. Take two particles whose distance apart is the Planck length. Now, because their distance is so small, the uncertainty principle says that they have a lot of energy. Okay. Right? The uncertainty principle says if things are very well localized, then they have a very large momentum. The fluctuations in the momentum are very large. So take two particles whose distance is known to be within the Planck distance, and that says something about their momentum. Their average momentum is extremely large, and from that you can compute what their average kinetic energy of these two particles are. That kinetic energy will be the Planck mass. So two particles, if you try to take two particles and localize them to a distance comparable to the Planck distance, the answer will be that that the energy that you have to put in to do that will be the Planck mass. So it's just uncertainty principle. We can work it out, but yeah. Right, okay. Let's take a rest. I'm going to tell you next about some mathematics. I'm going to tell you about the mathematics of conformal transformations. Why? Because that's the basic mathematical tool of string theory. Well, we have our choice. I can either tell you why there are 24 or 26 dimensions in string theory, or I can start to tell you about conformal transformations. We'll get to both of them at some point, but yeah. As long as it's not on Thanksgiving. Thanksgiving's always Thursday, so I think the answer is yes. Okay, we have 45 minutes, and I will try in 45 minutes to give you the easy version of why there have to be 26 dimensions in bosonic string theory. The easy version is not easy, and it doesn't really get to the root of it. The hard version is very hard. But that doesn't mean that we can't talk about it qualitatively, but I thought I would do what I call the easy version, which is not easy and not satisfying, but nevertheless is correct. Let's, and you know, when people see this, they walk away and say, gee, that's sort of magic, but in the bad sense. But it is correct, and it is sort of the way that the need for extra dimensions was discovered. It has to do, if you remember, in order to get the photon to come out right, we had to do something odd. We had to take the mass squared of the ground state of the oscillating string. You remember, let's take the open string. In the case of the open string, the mass squared had to be -1 unit. That was so that when we applied a creation operator to create the photon polarization, it came out massless. -1, 1 unit on top of that, gives us something massless. We haven't talked yet about how we get rid of this particle of negative mass squared. I assure you that can be gotten rid of. But let's not worry about it. Let's agree. The mass squared of the ground state is -1. Why is it -1? How do we get -1? Well, harmonic oscillators have 0-point energy. So the ground state energy of this vibrating string should be nothing but the sum total of all of the 0-point energies of the vibrating string. 0-point energies are all positive, and in fact they depend on the frequency. Anybody remember what the 0-point energy of a harmonic oscillator is? A half h bar omega, let's forget it, h bar, set it equal to 1. 1/2 omega, and do you remember the frequency of the nth harmonic oscillator? It was just n. N. Each one of the oscillating modes of the string, there's a string, each one of the oscillating modes, the nth oscillating mode has frequency n. So the ground state energy of the nth oscillator is just n over 2, in some units, is n over 2. Now this doesn't sound good. We have a lot of oscillators, one for each integer. We have to add up all that energy. It's not quite easy to imagine how we can add all this up and get -1. Right. So there's something strange going on, okay? And there is. But actually, we don't have to get -1. Well, we have to get to something a little bit different. Let's go back to the energy of a very, very fast-moving system. The energy of a very, very fast-moving system has, first of all, it has the overall momentum. Moving down the z-axis, it has the overall momentum. And then on top of the overall, and that's a conserved quantity. And we really don't care about it very much since it never changes during the processes that take place in particle physics. And then for a particle which is not moving, whose center of mass is not moving in the plane, what's the rest of it? Do you remember? The mass squared divided, I think, by twice the momentum. And that's why we began to identify the energy, the non-relativistic energy, with m squared rather than m. This was the energy. And to make precise this idea of very rapid systems which become non-relativistic, you have to let p become extremely large. Basically, you have to take the limit of an infinitely large momentum. In the limit of infinitely large momentum, this is the form that the energy takes. You say, well, wait, if I want to take the form of infinitely large energy, this thing just goes to 0. But what you really do is you take E minus P, you subtract the momentum from the energy. That's all right. This is a perfectly conserved quantity, never changes. If it never changes, you don't care very much about it. And then multiply the whole thing by, let's say, 2p. And that gives you m squared. This 2p here, the reason you multiply by 2p is that's got to do with time dilation. The faster a thing moves down the z-axis, the slower its internal motions go. The slower the internal motions, that means the smaller the internal energies. For example, if you have an atom, what's the ionization energy of a hydrogen atom? 13.5 electron volts or something, okay? Now you take that atom and you speed it up and you send it down. In other words, the energy difference between the ground state of the atom, let's not take the ionization energy, the energy difference between the ground state of a hydrogen atom and the first excited state is what? I don't know, 3, 4 volts, something like that? 3 or 4 electron volts. Now what happens as you boost the atom? What happens to the overall energy of it? It increases, of course, right? That's this. But what happens to the energy difference between the first excited state and or between the ground state and the first excited state? Does it get bigger or smaller? Smaller. And it gets smaller with this 1 over p here. And in fact, the energy of that atom, or the differences of energy between the atoms, are proportional to the square of the mass of the atom divided by 2p. So that's what this formula is. Well, we don't care about this piece. That just has to do with its overall motion down the z-axis. Just subtract it off. It doesn't have to do with the internal motions. And then the p in the denominator here, that's just associated with the slowing down of the internal motions. So let's just multiply through by it. And this is the way we really think of energy. This quantity is the energy, and it's proportional to the mass squared. Okay, the point is now that the actual energy of the ground state has an infinite piece, a piece with, or let's put this piece back. Let's not subtract this. Let's add this back on this side. Plus, what is it? Plus p squared plus 2p squared. Let me just get this right. P times E. Let's take P times E is m squared plus 2p squared. Okay? Notice that first of all is the interesting thing, which is the mass squared, which we're interested in, but there's also this infinite piece here. This infinite piece. So it's not really quite true that the energy has to add up to -1. It would be okay if it added up to something like -1 plus an infinite constant that was similar to p squared. So I'm going to show you how that works. I'm going to show you how that works, how you can add up 1 plus 2 plus 3 plus 4 plus 5, this is all the internal energy, and get something which looks like a constant, namely -1, which is what we want to get, plus an infinite piece that can be absorbed into something that's already there. This is a trick of physics that takes place all the time. It happens all the time in all kinds of contexts where you get some infinite answer and you don't know what to do with the infinite answer, but you realize that that the thing which is becoming infinite already has a constant piece in it that you just add the extra infinity to the constant piece. An example is the energy of vacuum, the energy of just the mass of a particle. There are self-energies, all sorts of things like that, where you can hide infinite constants into things which are already there. I'm not saying this is a satisfactory state of affairs. It's just something that we do all the time. The energy in this room, it has 0-point oscillations from all of the photons and everything else, not from the photons that are here, but from the oscillations of the electromagnetic field. How big are those oscillations? The energy? Infinite. What do we do with it? We just subtract it off by saying we could add a constant to the energy of the room and it wouldn't make any difference. So just get rid of it. It's the same thing here. We're going to get a constant piece which is just infinite but constant. As long as it's constant, it never affects anything. Plus a term which looks like this with an additional mass squared. Let me show you the mathematics, and we can then discuss another time the physics. The mathematics is tricky, but easy. The mathematics is just a question of adding up 1 plus 2 plus 3 plus 4. It's just a sum here. Okay? 1 plus 2 plus 3 plus 4. There's an overall factor of a half outside. That comes from the half h bar omega. But the basic calculation is to add up all of the integers. It's obviously infinite, okay? But let's see if we can extract out of that infinite piece an infinity plus something finite. This is always the way quantum field theory and relativistic quantum mechanics works. Okay, so 1 plus 2 plus 3 plus 4, this is not something we're going to easily add up, is it? So let's do something to it and then take a limit. Let's do something to it so that it makes sense and then take a limit. Let's multiply each one of these. Let's introduce a small constant, epsilon. E to the minus epsilon is a number less than 1. But when epsilon is very, very small, this number is close to 1, right? Okay. Let's add to it plus 2 e to the minus 2 epsilon. This is just a trick for making the sum converge. Each term in it, we're going to put in something which gets smaller and smaller, but when epsilon goes to 0, it'll just give us back the original sum. So epsilon is going to go to 0. In fact, you know what? Well, yeah, all right, let's leave it this way. 1 plus 2 epsilon, what's the next one? 3 e to the minus 3 epsilon plus 4 e to the minus 4 epsilon. But now, if epsilon is not 0, then the sequence of terms e to the minus epsilon, e to the minus 2 epsilon, e to the minus 3 epsilon do get smaller and smaller. Now, if epsilon is small, it takes a long, long time for them to shrink. So if we were just to plot the e to the minus epsilon, e to the minus 2 epsilon would be as a function of the integers, it would fall very slowly if epsilon is a small number. Right? But eventually, the e to the minus n epsilon will win, and it will make each term successively smaller and smaller, and you'll be able to add them up. Right? So what you do is you add these up, and then after adding them up, you let epsilon go to 0. Right? It's a mathematical trick. Right, so let's see what we get. It takes a bunch of steps, and I'll show you, but the steps are elementary. Okay, this can be written as the sum from n equals 1 to infinity of n e to the minus n epsilon. E to the minus 1 epsilon times 1, e to the minus 2 epsilon times 2, and so forth and so on, right? That's the sum. Now, the trick is to get rid of this n. First trick is to get rid of this n, and the way to get rid of this n is just to take the sum without the n in it and differentiate with respect to epsilon. What happens if we differentiate with respect to epsilon? What does the derivative with respect to epsilon give? It brings down minus n. All right, so this is equal to minus. So in other words, we really want to put minus here. This is equal to the original sum we were interested in, n e to the minus n epsilon. Okay, that's the first step. Next step is to observe that we can add the series up. This whole series is a geometric series. It starts out, let's just see what it is. It has an e to the minus epsilon plus an e to the minus 2 epsilon plus an e to the minus 3 epsilon which also can be written in another form. It's e to the minus epsilon times 1 plus e to the minus epsilon plus e to the minus 2 epsilon, and so forth. I pulled out a factor of e to the minus epsilon. Do you know what this is? Exactly. This is a geometric series, 1 plus a number plus the square of the number plus the cube of the number. And so we can add all of this up. And what do we get? We get e to the minus epsilon divided by 1 minus e to the minus epsilon. Okay, that's the thing that we want to differentiate with respect to epsilon. That's this, and put a minus sign in front of it. Okay, this is something you can do at home or for homework, but I'm going to show you roughly what happens. Oh, but in the end, we're interested in small epsilon. We're interested in small epsilon. So let's see, what do we want to do with that? Yeah. Let's expand it for small epsilon. Let's first expand it for small epsilon, and then do the operation, and let epsilon go to 0. We're interested in small epsilon. So what is e to the minus epsilon when expanded in terms of epsilon? 1 minus epsilon plus epsilon squared over 2, dot, dot, dot. We're only going to need things to power epsilon squared. We won't need things beyond that. And of course, there are more, but we won't need them. Now, what about the denominator? What's in the denominator? We have 1 minus. Okay, so let's write out e to the minus epsilon minus 1. I think it's plus epsilon minus epsilon squared. And let's go to the next one. I think we're going to need the next one, as you'll see. Epsilon squared over 2, right? What's the next one? Let me just check the sign. 1 minus 1 plus epsilon minus epsilon squared over 2. And the next one? Plus epsilon cubed over what? Over epsilon cubed over 6, right? Now, we have trouble. The trouble is the 1's cancel. The denominator is proportional to epsilon. Let's factor out 1 power of epsilon. Let's see. We want to take the derivative. This is the object whose derivative we want to take. Let's factor out a factor of epsilon in the denominator. Since everything in the denominator has epsilon, let's factor it out. 1 over epsilon. And then this becomes 1 minus epsilon plus epsilon squared. Did everybody follow that? Okay. Plus higher terms, but as I said, the higher terms are going to disappear when we go to small epsilon. They won't be important. Did I lose a minus sign? I was.
There's 1 minus the quantity 1 plus epsilon.
Well, I thought I got it right. All right, should we do it over? 1 minus, put in brackets, 1 minus epsilon plus epsilon squared over 2 minus epsilon cubed over 6. All right, everybody happy with that? Now, the 1's are going to cancel. And the minus times the minus will make plus, minus, plus. I have no idea if that's what I had written down before or not. Then we pull out a factor of epsilon, and that turns this into 1 minus epsilon over 2 plus epsilon squared over 6. All right, now the trick is we're expanding everything in powers of epsilon, but here we have a thing in the denominator. I don't want this in the denominator. I want in the numerator. So how do you deal with a thing in the denominator like this? You use the formula that 1 minus a small number, let's just call it s, is equal to 1 plus s squared plus s cubed, and so forth. Here's your s. Oh, did I leave out something? No, I think I got it right, did I? I think I did everything right. I think I did everything right. So what we do is we take what's in the denominator here, and we expand it to get all the epsilon dependence in the numerator. Let's see what we get. I think we're going to get 1 plus epsilon over 2 minus epsilon squared over 6. But then there's a term coming from squaring the small quantity here. If I keep things to order epsilon squared, all I'm going to get is, let's see, I think plus epsilon squared over 4, I think. But you can expand it out yourself, something like this. plus higher order in epsilon. No, I think it was epsilon squared. Mm-hmm. It was just epsilon squared. It was not epsilon cubed. No, the thing which was epsilon cubed in the denominator here became epsilon squared when I pulled out the epsilon here. And I was purposefully keeping everything to powers order epsilon squared. I know that the next order is not important. Okay, so let's see if we can combine this together. I think the chances that I'll get this right are negligible, but all right, so we get minus d by d epsilon, 1 over epsilon, times, okay, 1 times 1. Let's put in everything that you get from 1. 1 plus epsilon over 2 minus epsilon squared over 6. Oh, can we combine these two together? What's epsilon squared over 4 minus epsilon squared over 6? Epsilon squared over 12. Right? Okay. How did you do that so fast? Who did it? You didn't? What? Took me about 30 minutes to get that epsilon squared over 12. Okay.
3 minus 2, that's where you want. You know the common denominator is going to be...
I know how to do it. 1 plus epsilon minus, 1 plus epsilon squared over 12, right? That's this times this, this, and this. Then we get minus epsilon times 1, and then minus epsilon squared over 2. But then from here we get something of order epsilon cubed, and I'm not interested in keeping anything of order epsilon cubed. That's too high an order. I don't care about it. We'll see why in a moment. And then we have plus epsilon squared over 2, and nothing past that because the next one would be epsilon fourth. I think this is everything to order epsilon squared. Should it be plus? No? I think it should be plus, right? Yeah, right. Looks right. 1 times epsilon squared over 12. Okay, now, epsilon over 2 minus epsilon, that's minus epsilon over 2. We get rid of this. And these two cancel. So there's our formula right there. As we'll see, anything of higher order is not going to be interesting to us. Okay. Look at let's first focus on the one that's easiest. The easiest term is this epsilon over 2. It gets multiplied by 1 over epsilon. That means it's just 1/2. And what happens when you differentiate 1/2 with respect to epsilon? Is 0. So this is, we don't have to write it. It's not there. Okay. Now we have a term which is 1 over epsilon. That's bad news. This is something infinite at epsilon equals 0. And remember, we're going to go to epsilon equals 0. All right, what's the derivative of 1 over epsilon? Minus 1 over epsilon squared, right? Minus 1 over epsilon squared. Oh, and there's another minus sign here. So that's plus 1 over epsilon squared, I think. Yes. And then 1 over epsilon times epsilon, one of the epsilons cancel, and then you differentiate with respect to epsilon. What do you get? Minus 1/12. This is a famous formula which is usually stated half jokingly that 1 plus 2 plus 3 plus 4 plus 5 is equal to minus a 12th. They tend to forget about this term over here. Okay? And the reason is that this term combines, well, this term is an infinite constant which really doesn't, I would have to convince you that of what happens to it, it gets absorbed into the p squared, the p squared term in the energy, the infinite term in the energy, and a really careful analysis of it allows you to absorb this into something, into an additive constant in the energy that doesn't do anything. For the moment, you'll have to accept that. The real answer, the really right answer is that in good string theories, properly defined string theories, this isn't there altogether. But I'm not going to tell you why now. I'm not going to tell you why now. I'm just going to tell you this infinite constant is not important. You know the famous story of Dirac and Pauli, that Dirac calculated the vacuum energy and found out that it was infinite. And they said, well, since it's infinite, I don't care about it, we'll throw it away. And Pauli turned around to him and said, just because it's infinite doesn't mean it's zero. Right. Right. Well, in this particular case, Dirac wins. Dirac wins, but this is something we will have to come back to and explain why this 1 over epsilon squared. Remember, epsilon is going to go to 0. This is going to be an infinite constant. And in this particular case, the infinite constant really is not important. And I'm not going to pursue it right now. I'm going to tell you the answer is minus a 12th. Okay? Minus a 12th. Now, this is not yet a particularly good answer. This is not a particularly good answer yet. Remember, what we wanted to get was altogether minus 1. We wanted to get this minus 1, which when we excite it by 1 unit of energy will give us the massless particle. Okay? In fact, the minus a 12th is not quite right, and the reason is because of this factor of a half from the half h bar omega. So it's actually 1 over 24. 1 over 24. That minus 1 over 24 is the energy of the ground state, including the 0-point oscillations, but throwing away a certain infinite term, which we're going to have to explain away later. But, okay. How do we get, oh, have I left anything out? I left out one thing. Remember, for each mode, there is not one oscillator, but 2 oscillators, the A's and the B's. Remember the A's and the B's? The X oscillators and the Y oscillators. So actually, it's twice this. Twice this, 1 for the X oscillators, 1 for the Y oscillators. It's still not good. It's only 2 over minus 24. We really want to get minus 1. Right? How do you get minus 1? You say there weren't 2 dimensions of oscillation, there were 24 of them. Huh? 24 directions of oscillation plus the direction going down the z-axis plus time make 26. That's where the 26 is. All right? Now, this is a crazy story. At the time, nobody believed it, that this is a little bit too silly to be true. But, in fact, the mathematics did fit together, the mathematics. And this is the simplest way. This, which is fairly complicated already, is the simplest way to see, and it is historically the way it came about, that, that requiring, let's say there are d dimensions of space perpendicular to the direction of motion, and requiring this to come out to be minus 1, just so that when you excite it, you can get the photon That was the original argument about about D having to be 24, or the total space-time dimension having to be 26. Now, as I said, the arguments, this was hardly a convincing argument at the time. Its virtue is that it's easy to present, relatively easy to present.
What is the history? What was the history of this introduction? I mean, is that,
How did this come about?
yeah, well, I was just wondering, 1990s or?
Oh, God, no. 1969. Yeah, no, 69. No. No, this goes back to 1969, 1969, I would say. Maybe early 70, but I think it's still 69. Yes, well, by this point, people were just exploring the mathematics of string theory. And they had, well, experimentally you had the Regge trajectories, but at some point when the mathematical structure was put in place, people began to explore it for its own sake. All right? It was realized rather quickly that there was some kind of funny thing going on, that there was a spin 1 particle, 1 unit up from, but it didn't have all the states that it needed. It had 2 polarizations and not 3 polarizations. And it was realized rather quickly that this could only be the photon or something like a photon. But that then left the question, what was this 0-point energy that had to be -1? And it was realized fairly quickly that that required 24 dimensions of oscillation. Now, as I said, this was by no means a convincing argument. Other much more convincing arguments came about, but they were highly mathematical, really highly mathematical. And I'll tell you about them in words, but not now. We need one more mathematical
Is there a
concept.
similar trick to get 8?
To get 8. Yes. Yes, it's a similar trick to get 8. But before I tell you that, let me go back to the closed string. Remember, the closed string, you had to excite twice. You had to get spin 2. You had to hit it with 2 oscillators. That meant that the ground state had to have -2 units of energy. Okay? But now we have a problem. D over 24, if D is 24, is only -1. What's the answer?
48 minus 48.
48 is -2.
Why 48?
Get a -2. 1/12, right? Get the -2.
Yeah, but where do you, I know, but you only have 24 directions. We can't change the number of directions of space when you go from closed strings. No, the same theory has both closed and open strings. You can't change that. Right, you can't do that. No, we'll agree, the theory has 24 dimensions. Now what happens to the closed strings?
Circular polarized? Circular polarized?
Well, something like that. Remember, you have twice as many oscillators for the closed strings. You've got the ones that go around to the left, and you've got the ones that go around to the right. Everything gets doubled once again. You have not only an oscillation for every direction of space, but you have one for right-going modes and one for left-going modes. So in fact, it's true that you get twice as many, which means that the ground state energy is -2, which is just exactly the right thing, so that 2 units of oscillation will bring you up to massless again. That began to smell better. It began to smell better, but still far from a convincing argument. The real thing has to do with something called conformal invariance. So we're going to take up conformal invariance next time. What conformal invariance means. If you want to prepare yourself, learn a little bit about complex function theory. Very little, not much. We're going to do a very little bit. Learn what the Cauchy-Riemann equations are. If not, I will explain it. And we will come to why string theory is the theory of Turkish taffy. You know what Turkish taffy, you pull it this way, you pull it that way, you stretch it out that way, you stick it together, and somehow it all stays together. Conformal transformations. Anyway, I think we're finished for tonight. We've Cauchy-Riemann equations. Cauchy. Just learn a little bit about them.
For more, please visit us at stanford.edu.